good to welcome you to our Chapter 3. Today we're going to begin our discussion of correlation, linear correlation. And we're going to begin with just a review of a graph type that you probably have seen before, the scatter plot. In a scatter plot, both the x and the y-axis represent numeric variables. So when you see a dot in a scatter plot, really what that's doing is linking together two values for one subject or one case. On this one it might be something like, actually we're going to talk about this one in a minute, fat and calories. This one, believe it or not, is pretty famous. This scatter plot represents, I believe it's 2,000 data pieces, where the x-axis variable is the father's height and the y-axis variable is the son's height. You can see there's a lot of variation in there. But you can also see a pretty strong trend. As the taller the fathers were in general, the taller the sons were. And scatter plots are wonderful for doing that. They can show us about the relationship between those two numeric quantities. You'll see that in this scatter plot, someone thinks that a line might fit that model pretty well, and most of us would probably agree, although there are some points that are not very close to the line. This one, whomever drew this one, thought that a curve might be a better model for this, and you can see how it spreads out up there at the top. I truly can understand why you might want to put a curve there instead. This scatter plot we'll see again as well. However, think about this. That point way up in the corner, that it's some food that's got a huge amount of calories and also a huge amount of cholesterol. If that point weren't there, that plot might look a lot different, and that's something that we'll talk about in this unit as well. And we've added this one that plots cholesterol against sodium, another food thing that's going to make me hungry. This one also seems to have an outlier, one value that's way far off from the rest, and it might be said that without that value, again, this plot would have a totally different look to it. So those are the kinds of things that we're going to talk about as we go through our chapter on correlation. Let's begin here. The graph types that we've looked at so far in class, the dot plots, the stem and leaves, the box plots, and histograms, all of those are used to show the behavior of a single variable. It's called a univariate data set. That just means that it's a single numeric data set. So things like maximum longevity, we've certainly seen that one a lot. A single numeric data set. Scatter plots, however, display information about bivariate data. And as you think about where that word comes from, bi means two, so this is about two numbers, or data set about two numbers. In a scatter plot, each dot represents the values of two numeric variables about a single subject or case. You'll remember that the subject is what we are studying, okay? The variable, some quality about it. A scatter plot, I thought I'd give you some Big Ten basketball. Unfortunately, this is old data. It's from last year. You can see that dreaded Ohio State is at the top, or close to. We don't want them there anymore. But anyway, and it says let's create a scatter plot of games won versus games lost for the Big Ten basketball teams. A scatter plot is a graph like any other, so it deserves a title, and this one we can just call Big Ten if you'd like, and of course you can give it your own title. Usually we plot the first variable listed on the x-axis, so I'm going to plot games won down here versus games lost on the y-axis. And our first school, Indiana, at this time last year was 13-1. So over 13 up 1. That point represents the Indiana basketball team. Ohio State at 14-2 was close behind. And I'm going to go ahead and finish my plot. I'll catch up with you in just a few minutes. Here's my plot. You can see that we've got a dot for each team, with one exception. There were two data values that had the same records, two teams that each had the same record. That happened twice. So many times they'll show you in parentheses that that dot represents two data items. So that's the scatter plot. When we are describing the pattern in a scatter plot, and you'll remember we've described the shapes of histograms by looking at shape, center, and spread. In a scatter plot, center and spread perhaps are not as important, but shape, the things that we should look for are basically this. Are we linear? Are we curved? Or is there no pattern, no discernible pattern? And as you think about that, some of you might look at this one and say, yeah, that's pretty undiscernible. I could envision a line maybe that went that way, a line that went that way, and if we remove that point, it would be all over the place. So no pattern is an option. The trend in a scatter plot is talking about whether it's headed in a positive direction, up and up in both cases. So positive, which would mean that as x grows, y grows, or negative, as x grows, y decreases. And that's the pattern that we saw in our Big Ten scatter plot. The next thing that we want to talk about as we describe a scatter plot is the strength of association, and there are several words that you can use. Ones that come to my mind are a weak correlation, that is, there's not a very strong association between them, no correlation, moderate correlation, how much are they related, strong, and all kinds of adverbs that can describe those things. Moderately weak, right? Fairly strong. Those are descriptive terms for the strength of an association. I'd like to have you describe this one, or help me to. As you think about the shape, I would ask you to think, would a line fit here, a curve, or is there really no pattern? And I'm betting that most of us would agree that this is fairly linear. It's not perfect. Nobody said it had to be. Okay? The trend here, well, you can see that as the number of calories go up, so do the number of fat. That is, it's increasing in a positive direction. Or if you were to think about a line there, that line would have a positive slope. Okay? The strength of this association, here's where we may disagree. To me, this looks fairly strong. Okay? Some folks would call this moderate because it's spread out here at the bottom. This is your opinion, right? But as it always is in statistics, we ask you to support your opinion with fact. So I'm going to call this one fairly strong. And we've done our first description. I would ask you to pause the video, please, and write a description of this one in the lower left. All right, I'm guessing that many of you were influenced by the fact that there's a line there. Yeah, I think that looks pretty linear as well. This time we have a decreasing trend. When x gets big, y is getting small. So this is a negative trend, or decreasing. As far as the strength, I do think that these at the bottom they're quite a ways off from that line. I'm going to call this a moderately strong correlation, and just see how we get to decide with our descriptive words. We get to make our opinion known about these scatter plots. So moderately strong is what I would say there. You may not agree with me, and that's okay. This scatter plot, as we mentioned before, is fairly famous, and the reason it is so is that you can see tons of variation in there. Now, that's a very wide bar, but in general, folks, most of those points would fit into an oval like that. And according to the experts, if the pattern of points is fairly elliptical like that, or oval, then a line is a relatively good model. So they would say that that one has a linear shape. As far as the trend, it's going up, so this is positive or increasing. Now, it's up to you again how you label the strength of this correlation. I would say that this is moderate at best. Okay, I see the linearness of it, but it's not a real strong linear pattern. And the last one that I have down here, cholesterol on the x-axis versus sodium, I truly do not think that I see a pattern there at all. So I would say that there is no pattern here, or another word you could use there is scattered. The trend, there is none. And the strength of association, if I'm saying there's no pattern, then I'm saying there is no association there. And that's just my opinion again. Let's move on. We're the ones who are the statisticians here, or learning to be. And we've got to remember, folks, that just because there's a strong association between two variables, it doesn't mean that one causes the other to change. A direct cause and effect relationship is like that, where when one changes, one variable changes, it forces the other to change, or it initiates a change in the other. Folks, as you look at this, I hope that your mind is sending up little stop signs here. Calories, as calories increase, the fat goes up. I totally understand that, right? The question is, when you increase the number of calories in a food, does that cause the number of fat grams to increase? And I think that you would agree with me that that's probably not so, okay? In fact, it's more probable that as fat increases, calories increase. So whoever put this graph together, as fat increases, calories increase, at least that's my guess. Whoever put this graph together, I would say, put calories on the wrong axis, fat on the wrong axis, because we know that the causing or the independent variable is supposed to be on the x, the dependent one, the one that gets affected, goes on the y. So I think this one is kind of backward. There could be other factors, and you'll get a kick out of this maybe. They're called lurking variables. Sounds very shady and mysterious. Lurking variables that have an effect on both variables, as in maybe there's some other driver that some other way that increases calorie and increases fat. Maybe sugar, right? Or butter would be a good lurking variable for this thing. The amount of butter would certainly increase the number of calories and increase the amount of fat. A lurking variable is something that's in the background. It's not either one of the two variables here, but it's something that affects them both. I want to give you a for instance here, and this is true. This is fact. There's a strong positive association between a child's shoe size and his or her reading ability, which sounds kind of weird when you think about it. How could shoes have any effect at all on reading ability? When you need bigger shoes, does that mean that you have increased reading? Well, it doesn't cause an increase. However, aging, as the child ages, then both of those are affected. So as the child ages, or as they get older, then both the shoe size and the reading ability go up. Okay, so as the child ages, both reading and shoe size are affected. That's a lurking variable, age. Okay? Both reading and shoe size are affected. So I think as we end this little video that we want you to think about that. It isn't always true that just because the graph says this is on the x and this is on the y, the x thing doesn't have to make the y thing happen. We'll be asked to think about that a little bit more closely in some of the problems we solve tomorrow. That idea of cause and effect is an important one, and it certainly goes along with any discussion on scatter plots. Okay, I hope that you enjoyed this lesson, and we'll ask you to go out there and look at the U-Try as soon as you can. I hope you have a good evening.